be an or homomorphism. Be an or homomorphism. Or homomorphism. Or homomorphism. Or homomorphism of R modulo R modules R modules R modules K is equal to kernel F. K is equal to kernel F, and H is mapping from capital M to M by K. M by K, capital M to M by K. Be the natural homomorphism. Be the natural homomorphism. Natural homomorphism. Then there exists a unique Haar homomorphism. A unique Haar homomorphism. So G is mapping from M by K to N, M by K to N, such that F is equal to G circle of H. F is equal to G. So what is G and H are both are homomorphisms. So first one, let M to N be an R homomorphism of R modulo M. R modulo M, K is equal to kernel of M. H is mapping from M to M by K, be the natural homomorphism. Then there exists G M by K to N such that F is equal to G circle of H. So this is the mapping is a proof. So it is a called proof. So this is the mapping is. So what is the mapping is? So it is a mapping is. It is a mapping is. F is mapping from capital M to N. Capital M to N. Capital M to N. This is so is clearly M by K. So is a mapping. This is a mapping from G, M by K to N. This is H's map. So first one is further is G is an isomorphism. G is an isomorphism. If and only if F is an epimorphism. So epimorphism. So second, H is an isomorphism. So if and only if F is monomorphism. So this is a proof. Now proof. Natural homomorphism. So natural homomorphism. H is mapping from M to M by K. Is an epimorphism. So epimorphism is defined by H of X is equal to X plus K. For all X is belongs to M. So first of all, H of X plus Y is equal to X plus Y plus K. This is X plus K plus Y plus K. These are H of X plus H of Y. Next, H of XY is equal to XY plus K is a, so this is X plus K cosets are sent into Y plus K. H of X into H of Y. So H is a homomorphism. Next, for some For some x plus k belongs to m by k, then there exists x belongs to m such that h of x is equal to x plus k. H is onto. H is onto. So H is homomorphism, H is onto. So therefore H is homomorphism, H is onto. Therefore H is an epimorphism. Epimorphism. H is an epimorphism. An epimorphism. Epimorphism. Now A to n is by g of x plus k is equal to f of x. So f of x, what is f of x means can be written as this is f is mapping from m to n R homomorphism. X belongs to m. F of x is belongs to n is a codomain. So codomain that is called as. Now this is first we have to prove f is well defined. So well defined. Proof G is a well defined. G is 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 a well defined is equal. If two elements are equal, so x plus k is equal to y plus k. So according to definition, if and only if x minus y belongs to k, so where k is equal to kernel of f. Kernel of f. So kernel of f definition. So x minus y belongs to kernel of f. So this is equal only f of x minus y equal to 0. So f of xy equal to 0. F is homomorphism. F of x minus f of y is equal to 0. So f of x is equal to 0 plus f of y. This is f of x is equal to f of y. So f of x is equal to f of y. So what is our, this is f of x is means is equal to, if and only if f of x is equal to, this is g of x plus k is equal to g of y plus k. So what is the proof is x plus y, x plus k is equal to y plus k. We have to prove g of x plus k is equal to g of y plus k. G is well defined. G is well defined. G is well defined. G is well defined. Up to down well defined. Down to G is so G is 1 also. G is on to homomorphism. G is onto. Suppose we that f of x is equal to g of x plus k. G of x plus k is nothing but g circle of x. Nothing but g of h of x. G of h of x. What is the h of x is? H of x is equal to x plus k. G of x plus k is equal to what happened? F of x. So it's a clear. But we know that g circle of h of x is equal to f of x. G circle of h of x is equal to f of x for all x belongs to m. So f is g circle of h. G circle of f is equal to or g circle of h, or f is equal to g circle of h. This is called as g. It is a injective homomorphisms. Injective homomorphism, yes. One and homomorphism is injective homomorphism. It is a unique is there. So G is a map M by K to N R homomorphism such that F is equal to G circle of H. Then G of X plus K is equal to G circle of H and of X. G of G circle of X. So it is G of X plus K is equal to F. So equal to F of X is equal to H of X plus K. For every X plus K belongs to G is equal to G dash. G dash circle of H of X. G is equal to G dash. So G is equal to G dash. Therefore, G is a unique injective homomorphism. G is unique injective homomorphism. Now, now G of X plus K is equal to 0, then F of X is equal to 0, and X belongs to kernel F is equal to K. X belongs to kernel F is equal to K. So implies X plus K is equal to K element. So that 0 element in M by K is a monomorphism that G is isomorphism. G is an isomorphism if and only if G is an epimorphism. So G is epimorphism. If and only if F is an epimorphism, epimorphism. So F is equal to G circle of H. So next is H is an isomorphism. H is an isomorphism. If and only if H is a monomorphism. If and only if kernel of H is equal to 0. If and only if K is equal to singleton 0. Since so F is a monomorphism. So monomorphism. That is the theorem is completed. Is the one of the theorem we can do right here. Fundamental theorem of homomorphism. Theorem of homomorphism is let F is mapping from capital M to N. Exam? ఎవరు నేను ఇప్పుడే నేను ఆన్లైన్ క్లాస్లో కాపులు ఉంటారా నాకు 2 అవుతుందా 2:30 క్లాస్ అయితే 3కి ఇస్తాను లేకపోతే ఆల్జిబ్రానా నేను ఎందుకు రాలేదు నిన్న మరి అక్కడ డిస్టర్బ్ చేస్తారు Now, Fm to n be an R homomorphism, So of R modules, then f of capital M in a is an R submodulo M, submodulo of n, and the quotient ring and the quotient model modulo M by kernel F is isomorphic to f of M. So F is epimorphism. If F is epimorphism and epimorphism M by kernel F is isomorphic to capital N. Epimorphism that domain is equal to codomain. So codomain is N. So first we have to prove. Now so we have to proof given the statement. The statement is given that let F is mapping from capital M to N be an R modulo R homomorphism. So R homomorphism of R modules. Okay, R modules. You have f of capital M is equal to small f of x such that x belongs to capital M. So you can easily check them. F of M is an R submodulo of capital N. Okay, define a mapping. Define a map. G is a mapping from M by kernel F to F of M, capital F of M, defined by G by M by kernel F to F of, defined by G of X belongs to kernel F is equal to F of X for all X belongs to M. So this function G by M kernel F of X by G plus X plus kernel F is equal to F of X. So for any X belongs to, for all X belongs to capital M. So G is a function is well defined. So well defined function is elements are equal. First one we have to prove G is well defined. So well defined. So G is well defined. x plus kernel f is equal to y plus kernel f. Kernel f definition, if and only if ideal, x minus y belongs to kernel f. X minus y belongs to kernel f. By definition, f of x minus y equal to 0. By define kernel f. By defining kernel f, f is homomorphism. F of x minus f of y is equal to 0. F is a homomorphism or homomorphism or homomorphism. If and only if f of x is equal to 0 plus f of y. If and only if f of x is equal to f of y. F of x is equal to f of y is means g belongs to x belongs to kernel f is equal to g of y belongs to kernel f. So belongs to kernel f. Now G is a well-defined. G is well-defined. G is well-defined. G is a well-defined. Now, up to down well-defined, down to F is called as G is a well-defined. Can G is Haro homomorphism, also simple. Homomorphism is means G of x plus kernel F plus y plus kernel F is equal to G of x plus y belongs to kernel F. What is the definition is f of x plus y. F is homomorphism. F is homomorphism. F of x plus f of y. What is the f of x is g of x plus kernel f plus f of y, g of y plus kernel f. So g of xy plus kernel f is equal to f of xy. Since f is homomorphism, f of x into f of y. So f of x is equal to g of x plus kernel f into g of y plus g of kernel y plus g of y plus kernel f. So g of x plus kernel f plus y plus kernel f is equal to g of x plus kernel f plus g of y plus kernel f. G of xy plus kernel f is equal to g of x plus kernel f into g of y plus kernel f. G is homomorphism. G is a 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 homomorphism. Now, G is a well-defined. G is a monomorphism. F of m is the form. F of m is equal to small f of x is equal to g plus x plus kernel f. So, some x belongs to g plus x plus kernel f is equal to 0. Then f of x is equal to 0. So, x belongs to kernel f. X belongs to kernel f is means x plus kernel f is equal to kernel f. So is zero element. Ante m by kernel f. M by kernel is a G is a homomorphism. Is a isomorphism from 1 onto G by m by kernel f. M by kernel f is isomorphic to f of m. So f is onto f of m is equal to n. M by kernel f is isomorphic to n. So this is a theorem is called as fundamental theorem of R homomorphism. A second question. For any positive integer z by nz, and Zn are isomorphic to Z models. So next topic is Unit 6. Unit 6 is a direct sum and direct products. Direct sum and direct products. Now, N and K are submodels of M a ring or submodels of M over ring are the following: N by N intersection K. N and K, M and K are submodels of a module M over a ring are the following are: N by N intersection K is isomorphic to N plus K by K. N plus K by K. Second one, N if is N subset are equal to K, then M by N by K by N is isomorphic to M by K. Third, take second isomorphism theorem, third isomorphism theorem. Second isomorphism, third isomorphism theorem. So second and third isomorphism theorem in Haar models. So Haar models. So this is the proof. Proof is by fundamental theorem of homomorphism in previous. This is the function n plus k is whose kernel is an intersection K definition. Let f is mapping from n to n plus k by k. F n to n plus k by k is defined by f of x is equal to x plus k for all x belongs to n. It is a homomorphism. F of x plus y is equal to x plus y plus k, x plus k plus y plus k. Okay, this is f of x plus f of y. F of xy is equal to xy plus k, xy plus k, x plus k into y plus k, of x into f of y. Since f is R homomorphism, is an f is an R homomorphism. R homomorphism. we shall prove that we shall prove that we shall prove that f is onto. So small z plus k belongs to n plus k by k, where small z belongs to n plus k. Then small z is equal to x plus y, where x belongs to n, y belongs to k. Z plus capital K, x plus y plus k. Okay, this is y plus k కాబట్టి x plus k is equal to f of x. ఇక్కడ y plus k అయితే y plus k is equal to k. ఈ y plus k is equal. So f of x plus k is equal to f of x. So f of x. So therefore f is onto. F is onto. So f is an epimorphism. We can find kernel f. Kernel f is equal to those elements x belongs to n such that f of x is equal to k. So x belongs to n such that f of x is equal to x plus k is equal to k. So x belongs to n such that x belongs to k. So two elements are there, n and k. This is n intersection k. By fundamental theorem of Haro homomorphism, n by kernel f is isomorphic to n plus k by k. So what is the kernel f is n by n intersection k is isomorphic to n plus k by k. So n plus k by k. N plus k by k. This is a second isomorphism theorem. Now, third isomorphism theorem. Third isomorphism theorem. Third isomorphism theorem function defined by, suppose n subset r equal to k, k by n is equal to x belongs to n such that x plus n such that x belongs to k. We define the function quotient model m by n define. G is a mapping from m by n to m by k. M by n to m by k. They are defined by g of x plus n is equal to x plus k for all x belongs to m. G is epimorphism. G is homomorphism and G is a mapping from m by n to m by k is defined by g of x plus n is equal to x plus k for all x belongs to m. M is same. So g of x plus y plus n is equal to g of x plus n plus y plus n is equal to g of x plus y plus n. Okay. G is a homomorphism. Definition is x plus y plus k. So x plus k plus y plus k. This is g of x plus n plus g of y plus n. Next, g of xy x plus n. So xy plus n. G of x plus n into g of y plus n is equal to g of xy plus n. This is xy plus k. This is x plus k into y plus k. This is g of x plus n into g of y plus n. G is a homomorphism. G is onto also. For some x plus k belongs to m by k. So there exists x plus belongs to m by n such that g of is equal to x plus k. G, we can find G semi-morphism kernel of G. Kernel G is equal to all those x plus n belongs to m by n such that g of x plus n is equal to n, identity element. So x plus n belongs to m by n such that x plus k is equal to k. So g of x plus n such that m by n, so x belongs to k. This is nothing but k by n. By fundamental theorem of homomorphism, domain is m by n by kernel of G isomorphic to m by k. So what is the m by n is m by n by kernel G is equal to k by n is isomorphic to m by k. This is the fundamental theorem of third isomorphism. Okay. Next is theorem is 6.32. 6.32 theorem is M1, M2, Mn. M1, M2, M1, M2 to solve capital Mn. So B submodules of R module M. Then the following are equivalent. First one, M is equal to M1 plus M2 plus Mn. Okay. And Mi intersection J not equal to high. J not equal to high. J is equal to single one. Every element is x1 plus x2 plus xn. So with xi belongs to M. The exist endomorphism P1, P2, Pm of M such that Pi of M is equal to Pi of P high P1 plus Pn is equal to homomorphism. Pi circle of Pj is equal to 0 as to 2. So 1 implies is equal to summation of phi is equal to n to m in page number. You have to apply, can see me. This is not. Suppose 1 implies, suppose capital M is equal to no. M is equal to suppose I is equal to 1 to N, capital Mi. Mi intersection of summation J not equal to high Mj is equal to 0. M is equal to summation Mi follows that every element is M can be expressed as x1 plus x2 plus xn. Xi belongs to Mi to prove the uniqueness. X1 plus x2 plus xn is equal to y1 plus y2 plus yn. This is x1 plus x2 plus up to son plus xn is equal to y1 plus y2 plus up to son plus yn. So is the yn. Xi comma y1 belongs to Mi, 1 less than. Xi comma yi is belongs to m. Xi minus of yi is equal to summation of j not equal to high yj minus xj. So this is a belongs to Mi intersection of summation of mj is equal to singleton 0. Xi minus of yi equal to 0. Xi is equal to yi. Second implies to third. Suppose every element can be uniquely expressed as x1 plus x2 plus xn. So xi belongs to m for any 1 less than or equal to high less than or equal to n. Small pi is a mapping from m to m. Pi of x is equal to xi. X is equal to x1 plus x2 plus xn. Xi belongs to mi. Then clearly pi is R modulo homomorphism onto itself, into itself. Pi is endomorphism. So pi is equal to endomorphism. Endomorphism. Xj belongs to Mj. Pj of xj is equal to xj. Pj of m is equal to mj. For all one less than of j. X is equal to x1 plus x2 plus belongs to M. Xi belongs to M. X is equal to X. P1 plus P2 is equal to identity of Pi. Pj is equal to singleton 0. Now, I not equal to 0. 3 implies to 1. So, suppose P1, P2, Pn belongs to endomorphism of R. Endomorphism of R model M such that Pi of M is equal to Mi. P1 plus P2 plus Pn is equal to identity of M. And Pi circle of Pj is equal to singleton 0. I not equal to 0. First note that Pi is equal to Pi. Our identity Pi summation of Pi circle of Pi. Any X is equal to x1 plus x2 plus xn belongs to M, xi belongs to M. Pi circle of Pi xi is equal to Pi of xj equal to 0. Pi circle of Pj equal to 0, I not equal to 3 implies to 1. P1, P2 belongs to endomorphism M. Pi of M is equal to M. So Mi, P1 plus P2 plus Pn identity 1. Pi circle of Pj equal to 0, I not equal to 0. So Pi is equal to Pi is a old this one. Old this one. It is a summation of x is equal to Pi of summation of like this. J not equal to Pi of xi. So J not equal to Pi circle of Pj x of j equal to 0. Mi intersection of summation of Mj equal to 0. This is a, so we have the corollary theorem continuation same. Now next is the topic is a direct product. So definition of direct products is N is a R modulo M, N K or R model R modulo M. This is N is R modulo M, X Y belongs to R plus R. X comma y axis belongs to R. Now f of x comma y belongs f of xy is equal to f of xy plus f of x minus y comma 0, x comma x plus 0 comma y plus x comma 0 0 comma y. Okay. M by k and isomorphic to M by n isomorphism. This is the fourth 6.36 theorem. N is a submodel of R. M is a case direct sum. M by k, n isomorphic to n. M by n, k isomorphic to k. So this is k is the direct elements of n, k plus n is equal to m. K intersection is equal to singleton 0. So our fundamental theorem is k plus n is equal to m. K intersection n is equal to singleton 0 by m by k is equal to n plus k by k is isomorphic to secondary n by n intersection k is equal to n. So this is the next to tomorrow direct product will be start. direct sums. So the direct sums will start also.